input I mean that is all I had to say about the input current of the op. Is that clear? All right. So, now with this background, let us delve a little deeper into, I mean you must be wondering why the op amp's transfer function is whatever, right, this A naught by right. Of course, this A naught is understandable because of course, nothing in the world which is supposed to be infinite will be infinite. So, the A naught is a large number, but why is there a single pole dependence of the op amp's transfer function, right. So, to see that actually we need to, it turns out to be a practical reason and I will we will go into the internals of an op amp at the block diagram level, right. So, it turns out that the op amp basically works the following way. So, this is voltage 1, this is voltage 2, this current is, this voltage is converted into a current, okay, and this is GM1 times V1 minus V2. It goes into a resistance R1, right. Ideally, that R1 is supposed to be infinite and it also turns out that at the output of every gain stage there is also a parasitic capacitance CP1. Okay. So, this is for example, this is the simplest possible op amp that one can think of. So, what is the transfer function from Vi to, and of course, after this there is a voltage controlled voltage source with a gain of 1. Okay. So, what is the what is the transfer function of this this structure? GM1 is called the transconductance, because the first stage basically converts the difference in voltage into a current and that current flows through a large resistor R1. That CP1 is an undesired parasitic capacitance that cannot be avoided, right. And at the output V1 of the first of this stage, there is a voltage controlled voltage source. Why do we need the voltage controlled voltage source? We want to keep the output resistance, I mean ideally 0, in practice very small. So, what is the transfer function we get? So, VO by V1 minus V2 is nothing but GM1 R1 over 1 plus S CP1 over GM. Sorry, SCP1 R1. Okay. All right. So, what do you call? So, this is an example of. So, this basically this is can be written as some A1 by 1 plus S by omega 1, where A1 is GM1 into R1 and omega 1 is, I mean, and if we call this and omega 1 of course is 1 over R 1 C P, all right. I mean ideally of course we would like this A 1 to be very very large, of the order of 10 power 6 or 10 power 7, but unfortunately it turns out that in practice that the gain that you can get from a single stage is actually typically very small. So, let us say only 10 power 2, all right. So, so what do we you know so we want a gain of say 10 power 4 or 10 power 5, right. So, this is I would say this is 100 to maybe 500, that's basically the range of gain you can get from a single stage, okay. But we want a much larger gain. So, what do you think we can do? Well, the straightforward thing that suggests itself is to basically say, okay, well, if with one stage I can get a gain of I can get a gain of 100 or so, right. What should I do to get more gain? I should basically copy and paste this. So, this is GM some other transconductance, which will convert that voltage into a current, pass it through another resistor R 2, and then this is C P. Okay, and so this is voltage V 2. And this is voltage controlled voltage source. This is V 1. So, we already know that V 1 is nothing but GM 1 times V 1 minus V 2 times R V 1 minus V 2 times GM 1 R 1 by 1 plus S R 1 times C P 1, very good, multiplied by, now V 1 is going to get so this is V 1. Now, this is going to get this voltage is going to get converted into current in the second stage. So, that is going to be this going to be multiplied by GM 2, that is going to flow into R 2 over 1 plus S R 2 C P 2. This is, so that will be the gain of the second stage. So, this is the output V 2, which is also the same as V O. So, V O by V S or V O by V 1 minus V 2, therefore, is GM 1 R 1 times GM 2 R 2 by 1 plus S R 1 C P 1 times 1 plus R 2 C P 2, which is basically GM 1 R 1 GM 2 R 2 over 1 plus S R 1 C P 1 times 1 plus S R 2 C P 2. All right. So, so if we call this now, we have now A1 times A2. So, this is A1, this is gain A2, S over omega 1 times 1 plus S over omega 2. And I mean typically A1 and A2 will be of the same, I mean they may not necessarily be identical, but they will be roughly similar, right. So, if A1 is say 200 and A2 is 200, you basically have something like 10 power 4 times some 10 power 4 or something, right. Okay, and omega 1 and omega 2 will also be in the same ballpark, right. So, and if you want to get more gain, even more gain, what will we do? Well, it seems like so simple, you just keep adding more and more. If I add 10 stages, I will get like 100 power 100 to the power 10, which is 1 followed by a large number of zeros. So, it seems like a very simple thing to get more and more gain. And why do we need a lot of gain? Pardon? Why do we need the large gain in the op-amp? The virtual ground must be small, that is why we want a large gain, correct. So, but of course, by cascading stages we get the nice thing that we want, which is A1 times A2 times A3 times whatever, but in the process every extra stage is also picking up an extra pole, right. So, an n stage amplifier will therefore have n, at least n poles, right. Okay. Now, now our loop gain function is no longer, earlier the loop gain was A times whatever the feedback for A times f, the feedback factor. Now, what happens? The gain is frequency dependent. So, the loop gain is now also frequency dependent, correct. So, in the first order case, in the single stage case, what is the loop gain? The loop gain was A1 times f over 1 plus S over omega 1, correct. In the two stage case, the loop gain of S is nothing but A1 A2 times f over 1 plus S by 1 plus S over omega. All right. So, as you keep increasing the number of stages, so you have n stages, the loop gain function will become A1 A2 blah 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 times an, which can be a really large number, but unfortunately you will get 1 plus S over omega 1 plus S over omega n, correct. Is that clear? So, so now the question, remember what is the closed loop transfer function? Is what? 1 over f times loop gain by 1 over 1 plus loop gain, I mean loop gain over 1 plus loop gain. Now, it is now the transfer function will be loop gain of S divided by 1 plus loop gain of S, correct. And remember again, what are the poles of a transfer function? are nothing but the roots of the characteristic polynomial. So, basically in this case, you know, uh, uh, roots of 1 plus loop gain of S. Does it make sense? All right. And remember again, for stability, poles must lie in the left half S plane. Is that clear? All right. And from experience, if you have a feedback loop and if there is a lot of delay in the feedback loop, what do you think, you know, what do you think will happen? Okay, I mean, so to give you an analogy, right? So suppose suppose you are driving, all right. Driving is a feedback process, correct? Basically, you are looking at the road and then, you know, controlling the hand, the steering wheel and the brake and the accelerator and the clutch based on inputs that you are getting, and then, right. Okay. So, let us say you know, you are told to drive, but you are not going to be looking at the road, but we put a monitor there and a camera is looking at the road, and then whatever the feed in from the camera is put onto the monitor, correct. Okay. Now, as you keep increasing the delay between, let us say, you know, of course, the camera has to take a picture, the picture has to come onto the monitor. So, there is going to be some delay in that process, right. So, if there is a lot of delay, what do you think will happen? Right. I mean, you know, if the delay is very small that you cannot notice it, then, well, it's all everything, you know, it's almost like nothing happened. I mean, there is nothing different and everything works out well. But if there is a lot of delay, right, what happens? I mean, you are going to be, I mean, you are going to get into an accident, because what happens? Well, you know, you see a pothole, right, on the screen, right, but the pothole is, you know, is much closer than what you thought, because, you know, by the time you it comes onto your screen, your car has moved in front, right. Okay. And so, and you probably pass the pothole too, correct. And then only you are able to react only when you see the picture on the screen. So, therefore, you probably hit your brakes very hard, correct. But you already passed the pothole and the road is smooth again, and you have hit the brake, and so, you know, all of a sudden, therefore, you know, the person in the back who also is driving a similar car, what will happen to him or her? Well, I mean, he is seeing that you hit the brake only much later, because there is delay between, you know, his camera and his monitor also, and he is going to hit you, right. Okay. I mean, another feedback system is a telephone conversation with, you know, with say with another person, correct. So, obviously there is going to be some delay in the telephone line. I mean, no communication is instant, correct. So, you are talking, and then the other person on the other hand is taking a long time to respond. What happens? I mean, if it is if that delay is very short, then you are okay, right. But you are saying something and the other person takes a long time to respond, you know, what happens? I mean, let us say the other person says, hey, you know, you owed me money, what happened, right? And there is a long silence on this side. What does it, what is the other person going to say? Think. Yeah, so the other person gets very annoyed, right? Okay. So that is why there is basically, whenever you make a telephone call, I mean there is a limit to the standards say that the latency cannot be greater than you know, a few milliseconds, because that basically puts I mean just makes the other person angry, right, or annoyed, right. Okay. So, so the I mean so basically whenever there is a lot of delay in a feedback system, it can cause the system to become unstable, right. So, stability is something that you know, you have to always worry about whenever you take a system with memory and put it in a feedback, correct. Okay. So, I mean to take this taking this other way, you know, if you have very bad memory, then you will have a lot of friends. Why? Yeah, I mean, okay, maybe the other friend said something nasty to you, right, but you know, you do not remember, right. So, I mean, you will be very happy and you will have a lot of friends because you know, right. But if you remember everything in the past and on top of it you also analyze everything very carefully, right, which is basically saying you have a lot of gain, right. So, a small thing also you kind of keep thinking about it and you have a lot of memory, then what happens, right. I mean, it is very easy to find fault with everything that everybody has done, right. Okay. You understand, but so it is actually a blessing to have bad memory, right, because you know, a lot of bad things that happen to you, you just you tend to forget, right. I mean, that is why they I mean people keep saying time is a great healer, right. You know, what does it mean? I mean, it basically means that you do not remember the past, what happened 10 years ago, you do not remember it with the same intensity as what happened yesterday, right, and that is a good thing, right. Imagine, I mean, if you kept I mean, imagine what it would have been if it is the other way around, right. So, you do not remember what happened to you now, but I mean, this will basically only kind of hit you, you know, a lot later, but like what happened 10 years ago, it seems very intense, then you would be very unhappy, correct. Okay. So, so whenever you have a lot of memory in a feedback system, right, which is basically a lot of delay, right, and I mean, why is memory and delay the same thing? Well, you know, if you put in some input now and then the output is coming, you know, 10 minutes later, the information, where is it sitting in that 10 minutes? It's sitting inside the system somewhere, right. So, basically there is a lot of memory in the system, correct. So, if you have a lot of memory and you know, and you have a feedback loop, if there is no feedback, then it is okay, correct. Okay. Which is why, I mean, you know, when you do WhatsApp voice message, you do not care about delay, right. I mean, you know, you want to convey information, you know, I mean, see you at 8 o'clock at the restaurant, that is all that, I mean, you are not interested in hearing back from the other side, then you know, SMS or message is okay. But if you are carrying on an interactive conversation where there is a feedback loop, then the delay must be very small. So, whenever you take something with memory and put it in a feedback loop, the first thing you must check is if the closed loop system is stable, right. Okay. All right. And what is the meaning of stability? The meaning of stability must be the poles of the system, of the closed loop system, must be in the left half S plane, all right. And therefore, you know, and if you try to build a lot of, if you want to get a lot of gain by cascading stages like we have just seen, we said, oh well, it is so easy to get a lot of gain. Why don't you simply take one gain stage and put 100 of them in cascade, right. That is okay as far as the DC gain is concerned. But as we just saw, every gain stage is also associated with a pole, and therefore, when you cascade a lot of stages to get a lot of gain, you are picking up an extra pole for with every stage. And a pole is just simply a very complicated way of saying that the circuit has got memory, right. So, if you put a lot of stages in cascade, the forward amplifier now has got a lot of memory, right. On top of it, it's got a lot of gain, right. So, when you put it in a feedback loop, you know, what do you call, you have the risk of a closed loop system becoming unstable. It also points out another fact that, you know, if something sounds too good to be true, right, then it's probably too good to be true, right. Anything that sounds too good to be true is probably too good to be true, because we thought, I mean, getting 10 power 10 gain is so easy as simply cascading a bunch of boxes together, right. I mean, it sounds too simple, right. There must be some problem lurking, right. So, if everybody could build a gain amplifier with a gain of 100 million, then you know, people won't have to study for so long to get your high paying job, right. So, I mean, definitely there is something wrong, correct.